According to NASA's 2024 Human Exploration Roadmap, the first crewed Mars mission could launch within the next 2 decades, a window that may define the future of civilization itself. For the first time since Apollo 11, scientists believe we have both the technology and ambition to make it possible. Yet one question still divides every engineer, astronaut, and dreamer who stares up at the red planet. You're watching Astreon, journeys through the universe with real science and cinematic storytelling. Subscribe now for verified deep dives every week. The planet Mars has haunted humanity for centuries. It glows like an ember of destiny in our night sky, distant, cold, and almost within reach. For decades, our probes have mapped its craters, sniffed its atmosphere, and drilled its dust. But the dream has always been the same. A human footprint on another world. NASA's robotic scouts, from Viking 1 in 1976 to Perseverance in 2021, proved that Mars once held rivers, deltas, and chemical traces of life. Yet the gap between knowing and going remained immense. That changed in the minds of 2 men from 2 different eras, Buzz Aldrin and Elon Musk. Their ideas, separated by half a century, now form the twin pillars of the Mars blueprint. Before Musk ever dreamed of Starship, a man who had walked on the moon was already sketching a path to Mars. In 1985, astronaut Dr. Buzz Aldrin published a radical paper introducing the Aldrin Cycler orbit. The idea was elegant, a giant orbital vehicle that would loop endlessly between Earth and Mars, using each planet's gravity as a slingshot. Think of it as an interplanetary shuttle bus, efficient, predictable, and reusable. The Cycler would remain in solar orbit, while smaller taxicraft would ferry astronauts up to meet it during close passes. By borrowing momentum from planetary gravity instead of burning fuel, the journey could be cut to just 4 to 6 months, almost half today's chemical propulsion time. But the concept carried colossal engineering challenges. A spacecraft the size of an apartment block would need to be assembled in low Earth orbit or even on the moon. Docking maneuvers would occur at high relative speeds, far from Earth's safety net. Any miscalculation could leave a crew adrift in interplanetary space, a point of no return. Still, Aldrin's blueprint planted a crucial seed: use orbital mechanics and reusability instead of brute force rockets. He called the moon a point of departure, not a destination. In his view, Earth's satellite was the launch pad of civilization's next frontier. While Aldrin focused on orbits, aerospace engineer Dr. Robert Zubrin wrestled with practicality. He argued that Elon Musk's enormous Starship, a steel giant capable of carrying 100 passengers, was too big to be efficient for the first expeditions. Zubrin's answer: the mini-Starship concept, a scaled-down variant designed for easier landings and returns. His reasoning was mathematical and brutally logical. A smaller ship needs less fuel to slow down in the thin Martian atmosphere and less energy to lift off again. Under the Zubrin method, the full-size Starship would carry the mini-Starship into orbit, refueled by only 3 tanker flights instead of 10. Then, at a point called trans-lunar injection, the mini-Starship would undock and fly onward to Mars alone. Because it's lighter, it could aerobrake more safely and hoverland like previous NASA landers, avoiding the violent high-energy burns required for larger craft. Most importantly, it could return home without requiring 6 football fields of solar panels to synthesize methane fuel. Zubrin's math is eye-opening. A full-size Starship would need roughly 600 tons of propellant, demanding a 600-kilowatt power source running 500 days to manufacture the fuel on Mars. Shrinking the ship reduces that requirement by more than 90%, down to 1 football field of panels. Still massive, but plausible. His approach sacrifices volume for sustainability and safety. Each smaller mission builds experience, infrastructure, and confidence, the incremental path to colonization. Then comes Elon Musk, the man determined to skip the small steps and leap straight to the stars. SpaceX's Starship program, first announced as the Interplanetary Transport System, is built around one philosophy: scale. Instead of sending a few astronauts, Musk wants to transport hundreds of settlers and hundreds of tons of cargo per flight. Each stainless steel Starship stands 120 meters tall, powered by 33 Raptor engines and capable of reusability from booster to capsule. The entire system burns liquid methane and oxygen, a deliberate choice so fuel can be produced on Mars using in-situ resource utilization. But this ambition comes with staggering technical complexity. Before leaving Earth, each Starship must be refueled in orbit by up to 10 tanker flights. Once topped up, it performs a single burn to escape Earth's gravity and set course for Mars. During the 7-month cruise, the crew faces deep space radiation, isolation, and zero gravity, issues still under study by NASA's Human Research Program. Upon arrival, the danger peaks. Mars's atmosphere is only 1% as dense as Earth's. Parachutes are useless, aerodynamics barely work. Starship must perform a belly flop re-entry, using its entire body as a brake before flipping upright and firing its engines for a precision landing. If the engines ignite too soon, wasted fuel. Too late, catastrophic impact. There is no room for error, yet Musk insists the risk is worth it. He envisions a self-sustaining Martian city of 1 million people by the late 21st century. According to SpaceX projections, each flight could eventually carry 100 passengers and 150 tons of cargo, at a cost per seat comparable to a cross-continental flight, a claim still far from realization but backed by ongoing test campaigns at Starbase, Texas. Regardless of which plan wins, Aldrins, Zubrins, or Musks, survival on Mars depends on one factor: energy. Solar power works, but weakly. Mars receives only 43% of the sunlight Earth does, and global dust storms can darken the sky for weeks. Nuclear reactors, such as NASA's kilopower units, are under development to generate 10 kilowatts each, enough to run habitats and life support systems. Water, meanwhile, hides in the polar ice caps and beneath the surface. In 2018, the Mars Express orbiter detected subsurface lakes using radar. Extracting that water is vital, not only for drinking, but also for creating oxygen and hydrogen fuel. As NASA engineer Jennifer Trosper said in a 2024 interview, "Every kilogram we can make on Mars is one we don't have to launch from Earth." This principle drives all modern mission architecture. Make what you need where you are, from fuel to food to shelter. While SpaceX leads the private race, NASA, ESA, China, and India are shaping their own parallel missions. China's Tianwen-3 aims to return Martian soil samples by 2031, a prelude to human flight in the 2040s. NASA's Artemis program is laying the groundwork with lunar bases and gateway stations, testing life support technologies for deep space. As former NASA Administrator Bill Nelson told Reuters in 2024, "We see the moon as a proving ground. Mars is the horizon goal." International partnerships are quietly forming around this horizon. ESA contributes power modules, Japan develops supply landers, and Canada provides robotic arms. For humanity's first step on another planet, the mission patch may carry many flags, not just one. If current schedules hold 2025 to 2027, Starship completes full orbit refueling and first uncrewed Mars test flight. 2028 to 2030, NASA's Artemis 4 establishes continuous human presence on the Moon. 2033, NASA's Human Mars mission. Phase 1 launches with crewed flyby or orbital test. 2035 to 2040, possible first human landing, joint NASA-SpaceX operation or international consortium. Each milestone builds a foundation of logistics, experience, and political will. But as history shows, exploration timelines are flexible, budgets are not. NASA's current annual budget approximately $25 billion, with only a fraction devoted to human Mars systems. That's why private innovation remains essential. It fills the gap governments leave behind. The romance of Mars hides brutal facts. Cosmic radiation could raise cancer risks by 20% per year of exposure. Surface temperatures swing from 20 degrees Celsius to minus 120 degrees Celsius in a single night. And every kilogram of cargo must justify its cost to launch. Yet each challenge fuels a new generation of engineers. At SpaceX's Starbase, prototypes explode. And each explosion teaches more than a success ever could. In Pasadena, NASA Jet Propulsion Lab runs simulations of Martian soil for autonomous construction robots. In MIT labs, students refine life support loops where every molecule of air and water is recycled endlessly. Failure isn't the enemy, stagnation is. Buzz Aldrin's Cycler, Robert Zubrin's mini-ship, and Elon Musk's megaship all share one truth. They're bridges between imagination and reality. Each represents a philosophy of progress. Aldrins, disciplined and mathematical. Zubrins, cautious and adaptive. Musks, bold and exponential. Together, they form a roadmap not just to Mars, but to a new mindset. That space isn't a place we visit. It's where we belong. NASA's Perseverance rover still rolls through Jezero Crater, drilling rock cores that may one day be studied by human hands. At SpaceX, Starship serial number 30 undergoes static fire tests as engineers chase reusability milestones once thought impossible. And around the world, classrooms filled with young scientists run simulations of habitats that could bloom under a salmon-colored sky. The roadmap is messy, expensive, and uncertain, but it's real. Aldrin's equations, Zubrin's calculations, and Musk's prototypes are converging into a single narrative of persistence. As NASA Administrator Bill Nelson told CNN in April 2025, "We will go to Mars, not because it's easy, but because it's necessary for the next chapter of humanity." When that first crewed capsule touches the red dust, it won't be the triumph of one man or one nation. It will be the moment Earth becomes a multi-planet species, the greatest experiment our civilization has ever attempted. And that, as Buzz Aldrin might say, is magnificent desolation turned into hope.